All right. So you have an exam tomorrow. In recitation, I feel like we've done a lot of these administrative announcements already. Maybe I'll skip the majority of them just in the interest of time. I will note, though, another useful resource if you haven't, I don't think I've displayed this yet in class anyway. I know I've mentioned that it exists. But we have here another checklist similar to for our first test of kind of the key things that I think that you should be able to do, the key topics for each section. And so I'd invite you to go through this and just kind of look at each bullet point and make sure that you're relatively happy, performing each one of these bullet points. So if you haven't had a chance to look at this, this is another thing that's in my folder. Again, it's the midterm knowledge checklist. All right, before we jump into doing some specific problems to help us review, are there any questions, administrative or otherwise? Oh, sorry, yes.
Coordinates on that midterm exam field?
Spherical coordinates, not necessarily, but we had a 16.6 intro into parameterizations. And remember, that was, these other coordinate systems are just, different, we can consider them as parameterizations. So nothing specifically about spherical coordinates, just that, math has a natural tendency to build on itself. So maybe you're referring to, I do have one problem in here that looks spherical-esque. And you can either solve this in a 16.6 style, because ultimately this is asking for a tangent plane, which is not something that we did in 15.9 when we did spherical coordinates, or sorry, 13.9 when we did spherical coordinates. So tangent planes is fair game for like a 16.6 style question, or we can do this in a 14.6 style. So either one of these would be reasonable ways to find tangent planes. So just kind of another example of math building on itself. Okay, well then, why don't we go ahead and jump over here and decide what to take a look at. Wow, this jumped up quite a lot. Again, right before class, it was like at 12, and now we're at like 47. So it looks like the winner right now is problem number 8, followed by problem number 10. And then after that, maybe I'll revisit this page and just see if there is a new winner. Otherwise, we'll go to problem number 2. But we'll start with problem number 8 and then go to problem number 10. All right, so in this problem, we're using Lagrange multipliers. We have x squared y subject to the constraint of x squared plus y squared equals 1. For each, determine if it corresponds to a maximum, a minimum, or neither. All right, so Lagrange multipliers is, again, this came up in 14.8, so maybe I'll go ahead and, if you want to see more problems about Lagrange multipliers, this is 14.8 sort of stuff. You have to be given a function and a constraint, right? So we also had 14.7, which dealt with absolute mins and maxes, right? But then in 14.7, you didn't typically have a constraint equation. So that's kind of a key indicator. This one's nice. It says use Lagrange multipliers, but even if it didn't, right, the fact that we have a constraint equation kind of would push us towards Lagrange multipliers. So we need to calculate out a few things. In order to find mins and maxes, we're going to use a system of equations. And maxes and mins are going to occur when the normal vectors are parallel. So that's the first equation here. Plus, we need to be on our constraint equation. So x squared plus y squared should be equal to 1. So, of course, this second bit here is just kind of, it is what it is. There's no calculations to be done. But the first one here, we can actually do some calculations. So let's calculate out the gradient of f. So looking at f up here, if I calculate out the gradient, we need to take an x partial derivative. So we're going to get 2xy. Then we need to take a y partial derivative. So I'm going to get x squared. Next up, we also need to calculate out a gradient of our constraint equation. For this, we're going to have 2x, comma 2y. So our system of equations that we're going to have here, again, we have our constraint equation, but then we also need the x component of our gradient to be equal to the x component of the other side of the equation. So this is going to be lambda and 2x in that first component there. And then we also need the second components to be equal. So we're going to have what x squared is equal to lambda 2y. So these right here are going to be my three equations with three unknowns. And so this is what we're aiming to solve. So when I look at this, again, there are many ways of solving systems of equations. I like substitution. I like linear combinations, stuff like this in general. This second equation, though, also does have an x on both sides, right? And quite often when we saw this in class, this alluded to us breaking it up into cases. So we thought about, I'd really like to cancel this x. Sometimes you can cancel the x, sometimes you can't. So we need to break it up into those cases. When can you cancel the x versus when can't you? So the when can't you, this is if x is equal to 0. If x is equal to 0, remember canceling is just equivalent to division, right? And so you'd be dividing by 0, and that would be a problem. So we're going to have a situation, what happens if x is equal to 0? And we can solve out the system in that case. And then we're going to have a situation, what happens if x is not equal to 0, aka I can cancel it. And then we're going to have to solve the system in that case. So typically I find that, when x is equal to 0, or when one of our variables is equal to 0, that's typically a little bit nicer. And so let's go ahead and maybe look at this easier of the cases. So when x is equal to 0, this second equation here is just going to then say 0 equals 0. You can't cancel out the x, but it's not an incorrect statement or anything like this. If we were to plug in x equals 0 into my first equation, that's going to give me that y squared should be equal to 1, which implies that y is going to be equal to plus or minus 1. So as of right now, I have here 0, 1, and 0, negative 1 are possible mins and maxes. Now, reading the equation here, again, we're interested in using this Lagrange multipliers method. And for each solution, we're trying to find if it's a min or a max. In this case, it doesn't really ask us to find what the lambda values are. We're really just interested in the x, y coordinates. So at this point, I'd be happy stopping. But if we want to solve for what is the lambda corresponding to that, we can plug this into our last one here. And we're going to have what 0 is equal to lambda, and it's going to be 2 times either plus or minus 1. So this is going to correspond to when lambda equals 0. So if you're interested, what is that Lagrange multiplier that yields this sort of result? This is when lambda is equal to 0. This is important because, we had a quiz question, for instance, right, where it wasn't interested in all the possible solutions, but it was interested in a value for lambda. So sometimes it asks for lambda values specifically. Sometimes you're more interested in the x, y stuff. So in this case, we're really more interested in the x, y stuff and classifying these as mins and maxes. But you could imagine another quiz or exam problem where you are really interested in the lambda values. All right, any questions on this bit here before we move into the second part? Yeah.
Any case when you ignore the negative value for that, then case when you ignore the negative positive.
So the question is there any case where you would want to ignore the negative value, assume for y, right? That you would only want the positive one rather than the negative one? No, not that I can think of, right? In general, you probably don't want to remove solutions. So especially when they're the Lagrange multiplier questions like this, you want to figure out your full list of possibilities. So including the negative one is certainly the way to go. Sorry, yeah, question.
Critical points too.
So the question was, do we need to find critical points as well? And this is, I suspect, kind of akin to one of the web work problems where it had this with less than or equal to 1. And I'm not sure if it was exactly this, right? In this case, you would need to find your critical points inside of the circle first, when x squared plus y squared is less than 1. And then you would deal with when you're on the boundary and the constraint equation and all that sort of stuff. So in this case, the answer is no. You don't really care about finding your critical points when is both your x partial derivative and your y partial derivative both equal to 0, and finding your critical points inside of the circle, because in the statement of the problem, we're just interested when it's equal to 1. And this is consistent with all of the Lagrange multiplier questions that we did in class in 14.8 as well, right? We never really did looking for critical points. All right, good. Well, let's go ahead and move on into the second case then. In our second case, our second equation here, when x is not equal to 0, that means I can successfully cancel it. And so I'm going to cancel out the x, and I'm also going to cancel the 2, and then that's going to become y equals lambda. So again, this is me just writing down my second equation here. We also know in this case, right, we could plug these things into, and now we're going to use like basically a substitution method here. We could plug these into our third equation, and I'm going to get x squared is equal to lambda times 2 times, instead of y, I'm going to write another lambda. So this is going to give me x is equal to plus or minus root 2 lambda. So again, there's a lambda squared. So when I take the square root of that, that just gives me the lambda. When I take the square root of 2, well, it's just the square root of 2. And then remember, you need the plus and the minus. Okay. This also, by the way, tells me, since y is equal to lambda, you could also write down the equation x is equal to plus or minus root 2 y. So either one of these would be perfectly fine. Now I'm going to go ahead and take this and plug it into my first equation here. So in fact, let me go ahead, because y is equal to lambda, and I'm really interested in solving for x and y values. Let me prioritize that. And I'm going to write x is equal to plus or minus root 2 y. So again, just swapping out, instead of lambda, I'm going to write y. So then, again, my first equation was x squared plus y squared is equal to 1. And I'm going to swap in everywhere I see an x. I'm going to plug in this either plus or minus root 2y. Luckily, because we're squaring it, it doesn't actually matter if it's positive root 2 or negative root 2, because when we square it, either one of those is going to be 2y squared. All right, so now solving for y, I get that y is equal to plus or minus 1 over root 3. If I plug this in, I can also get my x values here, which is, again, I'm just taking my y values and I'm multiplying them by root 2. So I'm going to get several points here. X can either be root 2 over root 3 divided by 1 over root 3, where they're both positive. We could have the x1 be negative and still the y1 be positive. We could have x be positive again and y is negative. And finally, we could have both are negative. And of course, you can check these are on the circle, all that good stuff. And they satisfy all of our equations here. So in total, though, we have 6 points, right? So I'm going to need to go ahead and check. Because this is a closed bounded region, this x squared plus 1, y squared equals 1. We're on the circle of radius 1 here. The extreme value theorem is going to apply. And so we are going to be able to find our min and our max. And so it's just going to be the smallest of these is going to be our minimum, and the largest of these is going to be our maximum. And so again, we're plugging all of these into, our function is x squared y. So when I plug in 0, 1 or 0, negative 1, f of 0, 1, f of 0, negative 1, these are both equal to 0. When I plug in, I notice because we're doing x and squaring it, it doesn't actually matter if the x is positive or negative. They're going to yield the same result. So I'm going to say f of either plus or minus my root 2 over root 3. And I'm going to choose the positive y first. Now, whether y is positive or negative does matter because y is not being squared here, right? So when I square my x, I'm going to get positive 2/3, again, regardless if it was positive or negative. And if y is positive, that means I'm going to have 1 over root 3. And again, I'm taking x squared and I'm multiplying it by y. So we'd get something like this. If, on the other hand, my y was negative, I'd have, again, I'm taking my x and squaring it. So it really doesn't matter if it's positive or negative. It's going to yield 2/3 no matter what. But then my y just multiplies by that. And so this one's going to be negative. So here we have a positive value. That's going to be my absolute max. And here we have a negative value. That's going to be my absolute min. Because again, 0 is going to be right in the middle in that case. So of all the values from these 6 points that we could check, right? The largest is going to be this positive one, 2/3√3. And the smallest is going to be this negative one, -2/3√3. All right. Any questions on this one here? I guess, so we have 2 that correspond to max, 2 that correspond to min, and I suppose if I'm, answering the question as stated, these are neither. They're neither the absolute max nor the absolute min. They're still solutions to the Lagrange multiplier method, but they're not maxes or mins. Yes?
Part where you said if x is not equal to 0 and you got all of your points, I know how you got your x's, or
Okay.
the y's and the x's, but then why on the x side did you divide all of them by?
Why on the x side did I divide all of them by
You
√3?
have x plus or minus √2.
Uh-huh. Yeah. And I know what y is.
So then I guess when you're solving for x just by itself, is that just multiplying that √3 out to everything?
Exactly. Yep. So I'm taking this 1/√3 and replacing it up here for my y. And so that gives me the √2 times 1/√3. And so I can combine my fractions and just write it as √2 divided by √3. And again, there's lots of pluses and minuses. Good. Any other questions on this one here? Yes.
The very last part.
The very last part, yeah. So again, the last bit, and this is similar in both 14.7 and 14.8, is that you're gathering up a list of points. These points could be potentially your minimums, potentially your maximums, or potentially nothing, right? They could be just in the middle sort of deal. And so the last bit here is you have to take your entire list of points and feed them into your original function. I noticed that there were some folks who, on the quiz or something like this, maybe got confused and would sometimes, plug these into one of like the boundary equations or something like this, right? In which case you don't get really an interesting result. Remember, you're trying to figure out where the function has a minimum or a maximum. So you need to take these things and plug them into your original function. And when you do this one by one for each of these 6 points, right, you're going to get some result out. And the biggest of those results is going to be the maximum. So in this case, this one, and you can plug it into your calculator and get some decimal if you'd like. And the smallest of them is going to be the minimum. So in this case, this one here. All right. Yeah, one more question, then we'll move on to number 10. Mhm.
The gradient and you have to move it to go and you solve for the variables and then that will give you the point that you would have here.
Yeah. Yeah, so it sounds like what you're describing is like the 14.7 style. When we talked about absolute mins and maxes, so maybe in the second day or whatnot. And the first step here is to figure out critical points of your function. So critical points are where both f sub x is equal to 0 and f sub y is equal to 0. This is equivalent to the gradient being 0. And then you go on to check your boundary points or boundary curves. And this usually takes the majority of the time here, depending on how many boundary curves you have, right? If it's a nice problem, maybe you only have 1 or 2 boundary curves, but we saw in class when you start to have triangles or rectangles or all those sorts of things, you have 3 or 4 boundary curves to check. It becomes a little bit cumbersome. And then 3 is, again, assemble this list of maxes and mins. So, and check which is the largest and which is the smallest, similar to what we did here. So yes, this would be equivalent to if instead of saying you have a constraint equation, if you said that we have a region, So if you had this region when x squared plus y squared is less than or equal to 1, now you are on a closed bounded region. You're on this circle of radius 1 or it's inside. And basically all of the Lagrange multiplier stuff that we just did was, checking on this boundary. When x squared plus y squared is equal to 1, do you have any mins and maxes? So we did all the work for this. If you had where the x squared plus y squared is less than or equal to 1, you would need to include in this first bit right here and check for critical points. So yes, with only a slightly different, I mean, really all I need to do is change this equals to a less than or equal to. You now have one extra step. Yeah. Yep, exactly. So yeah, the question was, if you have a couple of boundary curves that intersect, do you need to include in those intersection points? And yes, those end up being the endpoints of the domain for these boundary curves. And so a big part of this was when you're checking for your boundary curves. Remember in class, there was, again, this takes a while. You got to check not only for your critical values on your boundary curves, but you also need to check at the endpoints. So exactly what you were describing there is checking at the endpoints. All right, well, let's do problem number 10 here, then we'll open it up to more questions. So we have this function here satisfies the wave equation. And so, yeah, I guess maybe I'll jump back really quick and just showcase that on this list here, I have a set of what I think are like the main skills that you need to have. And then also kind of just other vocabulary or knowledge that has come up that I wouldn't say is like super core, but every once in a while I see these things. I mean, we saw them on web work. They're fair game then for quizzes and exams and all that sort of stuff. So for instance, like the Laplace or wave equations. So this problem here is about the wave equation. This has something to do with partial derivatives from 14.3. We have definitions of closed and bounded regions, stuff like that. Again, I don't think it's like super core, but again, I've seen some true-false questions and that sort of stuff come up about those before. Extreme value theorem. Again, there's like 5 different ways that a line integral of a vector field can be written. Make sure you know all of those. And then there's lots of things that kind of are similar, right? A conservative vector field or a path-independent line integral or a potential function, right? They all kind of mean the same thing. Essentially that you're probably going to be using the fundamental theorem of line integrals. So these are some of the extra stuff, and the wave equation is on there. So the wave equation goes something like this. So functions that satisfy this partial differential equation are solutions to the wave equation. And A can be any constant here. So if there exists some A for which this is satisfied, some constant A, then we say that the function satisfies the wave equation. And then the answer would be true in this case. If it doesn't, then the answer is false. So we need to check. And it looks like, right, we see cosines and sines and we think of these as wavy functions, right? And so the temptation is to say, yeah, maybe it does, right? Because there's cosines and sines. However, when we check, and let's take a partial derivative first with respect to x, I'm going to get negative sine x. And then I take a partial derivative again with respect to x. Again, right now I'm calculating out this left-hand side. And I'm going to have what? Negative cosine x. And then I need to take a partial derivative with respect to t a couple times. So let's do that. So a partial derivative of, again, my function is this here. When I take a partial derivative with respect to t, again, this x is constant with respect to t. It's kind of like, again, we're using x's and t's rather than x's and y's, but they are independent variables from one another. So when I take the derivative here, I'm just going to get cosine of t. And when I take the derivative one more time, I'm going to get negative sine of t. And so the question becomes, can I go out and find a constant a so that this is always true, that cosine of x is equal to 2 squared or 3 squared or negative 10 squared times negative sine of t? And the answer is false, right? We can't, there's no constant that would do that. They're independent from one another. One has x's and one has t's. That's the first kind of red flag. The other is, well, one's cosine and one's sine, right? And those are not going to be just some scalar multiple of one another. If you offset it, that's true, but not if it's just a scalar multiple. So yeah, overall, this is false. And again, we had some Weber problems, I believe, testing this. So if you want to see a case where it's true, go back to the 14.3 Weber, I believe. Questions on this one? Yes.
Like the function work with this?
Would the standard,
Sine of AX minus omega t, like this thing.
oh, okay, so some physics wave equation. Yeah, I suspect so. Yeah. So I think if you have things that look like, and please double check. But I'll do some modified version of yours. So I'll just do sine of x plus 2t, for instance. I believe this should satisfy the wave equation. But again, please check. Okay, well, that's 8 and 10. I guess any other questions about this before we move on? All right. So then jumping back here just to see, hitting refresh. Wow, 71 now. So let's see, we did 8 and we did 10. Looks like next up is problem 2 and then problem 13. Problem 2 and then problem 13 and then maybe problem 5. So problem 2 first. Oh, okay, yeah. So this one, we're given a contour plot. And the question is, which function could possibly generate this contour plot? So this was back from 14.1. 14.1 had really 3 main topics. We had domains, we had ranges, and we had contour plots or level curves, right? So this was kind of the big 3. This was all before we started doing the calculus in 14.3. Whenever there's a problem that's multiple choice like this, and you don't have the answer that is none of the above, a legitimate way to solve, any such multiple choice question is via elimination, right? So if you can eliminate 4 of them, whatever your last one that you have is going to be the answer. And so rather than doing kind of very detailed plots of kind of each one of these, we can just try to eliminate ones that we know surely are not it. So for instance, if I was to take A here, and remember contour plots or level curves are the set of all XY pairs that yield some specific result, that yield some specific output for our function. So usually that output we say is some K for our level curves, where this is going to be some constant. And so if I was to rearrange this, I would get y is equal to x cubed plus k. And again, you can plug in all sorts of different k values. K equals 0, k equals 5, k equals negative 13, all of that sort of stuff. My question becomes, is there any way y equals x cubed plus k looks like a bunch of circles? And I hope the answer is no, right? X cubed plus k is going to largely look like my cubic function. So something like this. And then the plus k is going to move it up and down, right? So if it's plus 5, it's going to be up here. If it's negative 13, it's going to be down here. But right, it's going to be essentially x cubed moved up and down. So there's no way that this is going to be a. So we can exclude that. And again, you could, instead of leaving it as k, like I just kept the k there to say that it doesn't really matter what the k value is. It could be 0, it could be 5, it could be, again, negative 13, stuff like that. Again, you're just going to get a bunch of cubics. So if you'd prefer to set k to some specific values, you certainly can. So if maybe for the second one here, let's, maybe I'll set my k equal to 1, right? So again, here's b. I'm going to have 1 is equal to y secant of x. But again, you can leave it as k. So maybe I'll kind of display both of the methods over here, kind of simultaneously. Now, 1 equals y secant x or k equals y secant x, I have no idea what it looks like. Remember, in general, we are pretty good at graphing things if we have y equals. And so just like we did last time, solving y equals, in general, will help us graph this. There's a few exceptions, like x squared plus y squared equals 1. We can look at that and just say, it's a circle, right? And there's no reason to solve it for y equals. In fact, y equals maybe would look a little bit more confusing. But in general, y equals helps us graph many equations. So if I was to go ahead and try to get this as y equals, well, remember, secant is the same thing as 1 over cosine. So if I wanted to move that secant onto the other side, that would be the same thing as cosine of x. Or I guess you could write 1 over secant of x. But again, secant is already a reciprocal function. It's 1 over cosine. So that'd be 1 over cosine. And then instead of dividing by a fraction, you'd multiply by the reciprocal and get to the same spot. So either way, you're getting y equals cosine x. Y equals cosine x at this point, right? We could look over here, say is y equals cosine x, any way that's a circle. No, right? It's kind of this nice periodic function, goes back and forth, all that sort of stuff. Here, you can see that in the modified version for various k's, we're going to have k cosine x. So it's just going to be cosine of x's, but then scaled up by some factor, right? The amplitude is going to change. Maybe your amplitude's 2 or 5 or again, negative 13, stuff like this, right? But again, you're not getting circles no matter what. I hope that maybe I won't spend time on E as well, but E, again, I hope you can convince yourself you're not getting circles. The only one that I think that you're getting circles is probably C and D. C and D, both of these have an x squared plus y squared. If I was to look at C carefully, right, and again, I have k equals x squared plus y squared. I am getting circles in this case. K is essentially acting as a radius, right? So I could plug in things like 1 or 4 or 9 or, even things in between that, 5 and whatnot. And that's essentially acting as a radius. But my claim is that C can't possibly be the answer here. So even though we are getting circles, they're not the right circles. Can anyone maybe explain to me why these circles are not x squared plus y squared equals k? Go here. They're not centered about the origin. That's absolutely right. So these ones here are all centered about, right? You could write this as x minus 0 squared plus y minus 0 squared is equal to a radius squared. So I'll say the square root of k squared. Right? These are all centered about the origin. And yet, these ones here, they are seemingly centered about x equals 0 or the y-axis, but they're not centered about the origin, right? If they were centered about the origin, it would kind of look like a bullseye. Different radiuses, all centered about the origin. So I agree that C cannot be it. And so my answer here in this case is going to be D. This is really all the work that you need to do. However, it's nice to maybe see why this is the result. So why don't we take 30 seconds and see this. So again, I'm going to choose like 1 equals y over x squared plus y squared or something like this. You can choose a different k value. You can choose k equals 2. You can choose k equals 5. You can choose just k equals k and leave it arbitrary. And if we were to rearrange this, we're going to have x squared plus y squared is equal to y in this nice case. X squared plus y squared minus y is equal to 0. And so again, this x squared plus y squared means that it's going to be circular. But now in order to figure out what the center is, we need to complete the square. So we did this a lot in like 12.1, for instance. But if you want to see exactly what circle it's going to be, we're going to need to complete the square. And so again, you're taking your b dividing by 2 and squaring it, all that sort of stuff. So in this case, I think what 1/4 is what I'd like to add on to both sides. And this is going to give me x squared plus y minus 1/2 squared equals 1/2 squared, or we can leave that as 1/4. So we can see here that this is the y center here. For a radius of 1/2, it's being offset by 1/2 up. So maybe something like this here. And so this one's not centered about the origin. It's centered, again, along this y-axis. Essentially, these different k values are going to be skewing this up and down. Still, it's going to be a circle because you'll have the x squared plus y squared, but it's just kind of moving this up and down our y-axis, or x equals 0. But again, elimination is perfectly fine. All right, questions on this one? Yes.
Be like multiple choice, it would take quite a while to like draw them out, or?
Yeah, so the question is are contour plots likely to be multiple choice just because of the time it takes to draw these things out? I'd say, yeah, in my experience, I do see them more often as multiple choice or true false rather than a standard response. Because then you need to be kind of very specific, right? How many level curves should you draw? And you have to also decide, are you going to let students choose which level curves, what K values to choose, or are you going to choose for the students, right? Stuff like this, right? Do you want all the pictures to look exactly the same, or do you want there to be some freedom? And so, yeah, quite often they just don't make great standard response questions. So it's possible, but it's unlikely, right? Good. Any other questions? All right. Sorry, I forgot which one it was. Problem 13 was next. Suppose that C1 is the line segment from 0, 0 to 1, 0. C2 is a portion of the parabola from 0, 0 to 1, 0. Then these line integrals are equal to one another. So in one case, we can include them on both of them on one plot here. 0, 0 to 1, 0, a line segment. Maybe I'll do in blue here. So there's my C1. C2 is a portion of a parabola, but it hasn't even told me like which parabola or any more information other than that there's some parabola out there that goes from 0, 0 to 1, 0. So, okay, I guess I'll do something like this. And the question is, are these line integrals equal to one another? What do you guys think about this one? So the answer that I'm hearing is yes. And coming from 16.3, I would absolutely, agree that it's, we learned about something called path independence in 16.3. And we talked about how this deals with, it doesn't matter necessarily the path that you take, only your starting and ending points when calculating out these line integrals. But that was for 16.3. And remember, 16.3 doesn't work for every single line integral out there. What did you need in order for the fundamental theorem of line integrals to work in 16.3? Yeah? Exactly. You need a conservative vector field. So this is that bit in the checklist here. One of them anyway, right? That there are lots of definitions that are closely related. So you could say that, yes, you needed a conservative vector field. You could have also said that, right, you need our vector field to have a potential function, right? And in that case, right, you do get a path-independent line integral. So I guess my last question, if this is all the way true, or if it's possibly false in some scenarios, is, are all vector fields conservative? And the answer is sadly not. So there are certainly vector fields out there, and you can make them quite easily, right? So our check for vector fields would be, again, if you have some P and Q, the component test says that P sub Y needs to be equal to Q sub X, right? So, I mean, you could build these things quite easily by doing, for instance, 0x. This right here is a non-conservative vector field because, well, when you take your first component, P, and take a partial derivative with respect to Y, you get 0. When you take your second component, Q, and take a partial derivative with respect to X, you get 1. So 0 is not equal to 1, no matter how hard you try. And so this is not going to be a conservative vector field. And so in this case, if you were to figure out a specific parabola and all that sort of stuff and set this up, when you calculate out these two line integrals, you'd get different answers. And so the answer here is going to be false. when it comes to mathematical true-false statements, false kind of has an unfair advantage. Because, you know, in mathematical true-false statements, is this statement always true? In which case it's true, and you could almost like make it into a mini theorem or something like this. Not a terribly useful theorem in this case, but you could make it into a mini theorem and prove it and all that sort of stuff. Or are there some cases where it's false? So is it always true versus are there some cases where it's false? And so, I mean, just my own experience taking math classes and whatnot, I would say that, you know, if you truly have no idea on a true-false question, you know, it's probably not quite a 50-50 on true-false, right? You want a little bit of a weighted coin towards false. And I'm not sure what exactly the weighting should be, if it should be 60% or 70% or something like this. But again, kind of false has a bit of an unfair advantage, because once you find one case where it's wrong, where it's not equal, right, then it's false. It's a false statement. So, all right. Any questions on this one here before we move on? Yeah. So yeah, the question, yeah, it is false. And it's because we don't know that our vector fields are conservative. If it added one more sentence, right, suppose that F is a conservative vector field, then the answer would be true, right? We would, everything about the fundamental theorem of line integrals is satisfied here. So yes, it'd be f of b minus f of a in both cases. And so we'd get the same result. However, nowhere in here does it say that F is necessarily a conservative vector field. So it's just any old vector field. And so because of that, I don't know if it's conservative or not. And so I could certainly construct situations where this statement is false. Good. Any other questions? All right. Well, let's jump back here one more time. Let's see, we did 8 and 10 and 13 and 2. It looks like problem 5. Problem 5 has quite a few votes. Oh, okay. So yeah, this is the one that I was kind of talking about beforehand. So yeah, formally, this stuff about spherical equations is not a focus of our midterm exam. However, in order to solve this problem with tangent planes, right, again, the majority of the work is going to be done either in 16.6, which is when we had parametrized surfaces. Let me go ahead and just maybe write some of this stuff down. And we could get a normal vector by taking a partial derivative with respect to one of our variables, a partial derivative with respect to our other variable, and then cross-producting them. So this would give us our normal vector for our tangent plane. So in this case, our variables, once we plug these things in, would be, instead of s's and t's, they would be p's and thetas. But you would absolutely do this using a 16.6 style. Or the other option in this is that you could use a 14.6 method, in which case we found that our normal vector was equal to the gradient of our implicit surface equation. So there's actually two different ways to solve this one. Given how much time we have and whatnot, I would say this 14.6 one is a little bit nicer. And so we're going to go ahead and do that. But I invite you to try maybe the 16.6 method after class. So, okay, why don't we find the equation for the tangent plane? The low-hanging fruit here is for any plane equation, we need two things. We need that normal vector, and that's going to be the bulk of the work. But we also need a point that this tangent plane is going through. And this relies on us being able to get an x naught, y naught, z naught. Now, in our case, we are given some specific values that we're interested in. However, they're not in the x, y, z coordinate system, right? And so we can easily turn these into x, y, z information just by using our formula sheet, right? So for instance, x is supposed to be equal to rho cosine theta sine phi. And so we could plug these things in here, what, 2, and cosine of pi is going to be -1, and sine of pi over 3 is going to be √3/2. So we're going to have, what, -√3. We can get a y coordinate by, okay, on our formula sheet, we get rho sine theta sine phi. This is going to be 2, 0, and who cares? It's 1/2, but nope, it's still the √3/2. There we go. But again, the sine theta, sine of pi is 0. So we're getting 0 there. And then finally for z, we have rho cosine phi. So rho is going to be 2. Cosine of pi over 3 is going to be 1/2. So this one's 1. So now we've converted our spherical point of interest into our Cartesian point of interest. And so we can swap out here, instead of our x naught, y naught, z naught, kind of this special point here, √3, 0, 1. All right, so that's the relatively nice stuff. Now we need to decide on how to get our normal vector. And again, this is where you have some choices. You could do a 16.6 method, but I think the 14.6 method is going to be a little bit faster. And so in order to do this, right, 14.6 was all about stuff in Cartesian. So I need to take my curve here, or my surface here, and figure out how can I write this as a Cartesian equation. And in the interest of time, I mean, we've done this before as well. I'll just tell you that an easy way to do this is to multiply by rho on both sides. And in that case, you get x squared plus y squared plus z squared is equal to 4z. In order to get normal vectors, thanks to the 14.6 method, remember you need to have all of your variables on one side and you need to have a constant on the other side. So you need to have f of x, y, z is equal to some k, some constant. So I'm going to set this up, x squared plus y squared plus z squared minus 4z is equal to 0. And so now we can just find the gradient, and that's going to give us our normal vector. So what? 2x, 2y, 2z minus 4. We can plug in our point of interest. So at this, what? Negative √3, 0, 1. We get negative 2 √3, 0. And when I plug in 1 here, I get negative 2. So again, I need to find the normal vector at our specific point of interest. We found that that point of interest was negative √3, 0, 1. So this right here is our normal vector. So I'm just going to go ahead and take this and plug it into my plane equation. Everywhere I see an A, a B, and a C. This was negative 2 though, right? Yeah, negative 2. There we go. So this would be my final answer. All right. Well, I think that's probably a good place to end. Just, similar to our first test or whatnot, any of the problems that we did not get a chance to talk about in today's class, I will go ahead and write up the solutions for those and hopefully post them by 4 o'clock today. It might be slightly after that just because I have my office hours, but I will post the solutions for all of these problems that we didn't get to still today. So check D2L on what problems we didn't get to in class document, and the answers will show up. So they'll be there. All right. Well, with that,